some practice questions on Stokes theorem. So what Stokes theorem does is that it relates the surface integral of the curl to the line integral around the boundaries. So now what they want us to do in this case is they want you to evaluate this surface integral. Now, how are we going to do this one? But instead of doing the surface integral, in this case, what we're going to be using is we're going to use the line integral. And when you look at the S is a part of a cone where y goes from 0 to 3. Then boundary is when y goes 3, it creates a circle. So in fact, then what I'm getting is 9 equals x squared plus z squared. So what I can do is I can convert this one into r, can be equal to x can be 3 sine t, y is equal to 3, and z is equal to 3 cosine t. And then where t goes from 0 to 2, pi. All right, now then let's try to look at this one. Then we need to rewrite f based upon these three things. And then I'm going to just leave some space for r prime. F now then is equal to, what is the x component? I mean, it was x squared, so this one has to be squared, and this one has to be cubed, and then multiplied by this one. So then we get 3 is 1, total 3, and then total 6 times. So basically it becomes 3 to the 3 to the, what you call it, 6th part, which is 729. And then sine has been squared. And we have cosine t. That's the first one. How about the second one? Second one is sine here. But x, y, z are all multiplied together, so we get 27 sine t and then cosine t. It looks very complicated. Sine, cosine within the sine function. Third one is this x, y, z, which is 27 sine t cosine t. Now, so that's basically what we have. But we need to figure out the r prime. What is r prime here? Then here what we end up getting is 3 cosine t. And then this one becomes 0. And then here negative 3 sine t. So what we're going to be doing is we're going to do line integral of f dot r prime dt. So which is equal to, when I multiply these two, so what do I end up getting? 2, 1, 8, 9, and then sine squared t, cosine squared t. Second one becomes 0, and third one, in fact, becomes minus 81 sine squared t, cosine t. It goes from 0 to 2 pi. All right, so now let's look at this one together. The numbers are somewhat large, but I remember sine times cosine is in fact is equal to half of sine of double angle formula. So I can rewrite this one as sine of 2t over 2 squared. That's essentially what I have here. This one I can usually use up. So then when I take the integral, wait a minute, how am I going to do this one? I'm going to bring this one out to the front. So we have 2, 1, 8, 9 over 4. That's how I'm going to begin. But what is sine squared? If you remember, sine squared of 2t can be expressed as, let me change the color for this one. Can be expressed as 1 minus cosine of 4t over 2. So what I can do is I can bring this 2 to the front, and it becomes 8. And then 1 becomes simply, when you integrate this one, 1 becomes simply t. And this one becomes minus sine of 4t over 4. That's the first one. Second one here, I can use the u sub, where u equals sine of t, then du becomes this portion. That's du. So we get minus 81 sine q t over 3. So that's basically the expression that I'll be end up getting. Now, which goes from 0 through 2 pi. Now then, when you realize that whether I plug in 2 pi or 0, you know the sine value in this case will always give me the same value. So these two things will cancel away. Only thing that remains is this one. So our final answer becomes 2,189 pi. 2 cancels out with 8 over 4. So that becomes our final answer. Alrighty, let's move on to the next problem. Number 6. So same deal here. And then in this case, S is a hemisphere. So that means in this case, what we end up getting is the boundary would have been when x equal to 0. When x equal to 0, you get to see that this one now becomes y squared plus z squared is equal to 1. Unit circle. That's what we end up getting. Now, but the fact that they want us to use the equation 3, then we're not going to use the hemisphere, but rather we'll be using a circle on YZ plane where x is equal to 0. Because if you remember, curl of the first surface is equal to second surface of the curl. That's the equation 3 that they're referring to from the textbook. So what I want you to do at this point is, knowing that, one thing that which we get to realize is we need to find the curl first. To find the curl, based upon this one, and then x dz, and the first one is e to the xy cosine z and x squared z and xy. So let's look at the first one. What do we realize about the first one? So we get x minus second one is x squared. That's the first component that we end up getting. How about the second component? So here we get negative e to the xy sine z, this one, and then minus y. Thirdly, what we end up getting is 2xz minus x e to the xy cosine of z. That's kind of long for the third one. That's what we end up getting. But in this case, what is our normal vector? Because what we need to do is we need to figure out the normal vector here. And then based up, so this is curl. We just figure this one out. curl has to dot to the normal of the surface. So what is the normal vector? We are assuming the circular disk on the yz plane. So that means that's equal to simply I. So when I dot curl dot ds, is simply become now x minus x squared dA. Now, but the thing is, we have to realize that at this location x is equal to 0. So this one becomes simply 0 dA, which becomes 0. So that becomes our final answer. All right, so so far previous two questions, what we talked about was we were using the surface integral. We are evaluating the surface integral through the line integral. How about the other two? In this case, they want you to evaluate the line integral, but we're going to be using the surface integral. So let's look at number 8 first. So this is what we have. We don't want to go through the boundary, then we have to do 3 different integrals. Instead of doing that, let's try to just go for the curl. How do you calculate the curl here? So I, jk, partial against z, and then so here we have e to the negative x, e to the x, e to the z. So what is the first component? Boom, boom. None of them works out, so it becomes 0. Now, how about the second one? The variables don't match, so it becomes 0. Third one becomes e to the x. Oh, that's the only thing that we have. So curl is simply 0, 0, e to the x. That's essentially what we have. Now, then let's try to look at the our domain here, surface. So I can easily solve for z. Z is equal to 1 minus x minus y over 2. I can solve it in that way, where x goes from, in case of x, zero through 1, and then if you to sketch the surface based upon the x-axis and the y-axis, you can see the x-intercept would have been 1, and the y-intercept would have been 2. And then the equation of the line here would have been y equals 2 minus 2x. That's basically what we end up getting. So you can see that y goes from 0 through 2 minus 2x. Alrighty. So then we know that this line integral is in fact equal to the curl dot ds. But one thing that which we get to realize is then since this is my surface z, we should remember this one was in fact equal to negative dz dx, negative dz dy, and then 1. But the thing is, since x and y component is equal to 0, when I dot this one with this, we only left with the last component, which is equal to e to the x dA. Now, but in this case, one thing that which we get to realize is this, that the when you and the boundaries can be rewritten as e to the x, dy dx. Y goes from 0 to 2 minus 2x. X goes from 0 to 1. Now, I'm going to continue over here. Since I don't have anything here, this is the same thing as 0, 1, 2 minus 2x, and then e to the x dx. Of course, in this case, what we have to do is we have to integrate by parts. So I'm going to say u, and then dv, mv, du. All right, so let's look at this one together. I'm going to set u as 2 minus 2x. That gets me du as negative 2 dx. dv is e to the x dx. And this one is simply e to the x. So what we end up getting is first 2 minus 2x times e to the x minus integration of this one. But that you get to realize that a negative 2 times e to the x, when you integrate this one, still negative 2 times 2 to the x with another negative plus 2 e to the x. That goes from 0 to 1. Now, so when you plug in 1, what do we end up getting? This one becomes 0. So we get 2 times e to the 1 power. When you have 0, then what I'm end up getting is this one is equal to 0. And then, so this one is equal to 1. So we get minus 2. And then this one is what? Another minus, so we get minus 4. Becomes my final answer. All right. Let's look at the last example here. Number 9. Same deal. So what they want us to do is they want us to use the, line integral. But we will be using the surface integral. So first we need to do the curl. yz 2xz e to the xy. For the first component, we get x e to the xy for the first one minus 2x. That's the x component. How about y component? Y component is y and then minus y e to the xy. That's basically what we end up getting. Now, the last component here, we get 2z and then minus z, which is just 1z, but that's basically what our curl is. Now, and when you describe the surface, you can see that the surface that which we are looking at is x² plus y². It's less than or equal to 16. Basically, we are looking at the disk at z is equal to 5. And you can realize that normal vector at this point would have been equal to k. Now, then we get to realize that normal curl f dot n, before we do the dA, which first two component just disappears, and we gotta multiply 1 times this one. Then we get 2z minus z, which is equal to z self. But z is equal to 5, so this is equal to simply 5. Then our curl f dot ds now becomes simply 5 dA. But what is the area? So this is equal to 5 times area of that circle, which is equal to 16 pi, so we get total 80 pi. becomes our final answer. Alrighty. With this one, I'm going to close up, and I'll see you later. Bye.